Maybe I can add already. So for the agenda, the idea is we'll start with a quick intro on the whole repricing effort. I will show some slides, and then we'll start doing the deep dives for EIP. So I have picked the champions of the EIPs, and I will ask for them to present in order to make sure that we keep on time and we have time for all the EIPs. I'm giving 5 minutes for each EIP, and I will be sorry, but I will try to be very strict with time. So if your 5 minutes are up, I will warn you, and I will have to move to the other EIP. So on that note, I think I'll start by sharing my screen so we can do the quick intro. Okay, so let's talk about repricings in Amsterdam. So first, I wanted to have a common view on why it is important to do this now in Amsterdam. And I think there are two main reasons. So the first one is that Amsterdam is all about scaling the L1. And so this is, let's say, the focus of the fork. And I think that pricing has a direct impact on scaling. And this is achieved by harmonizing operations that currently are not harmonized. So for instance, the compute operations, they don't have the same performance in terms of million gas per second. State creation also doesn't have the same cost depending on the operations. And also, for instance, data from access lists are free, while from call data, you have to pay for the data. So there's tons of these harmonized operations across different resources, and this leads to single bottlenecks. So by doing this harmonization, we are removing these single bottlenecks and allowing for the EVM to perform in a more harmonized manner. So we are removing these single bottlenecks. So this is a diagram that Ansgar did in a talk a few months ago, and it's essentially showing that you have like all these resource, or for a single resource, you have all these operations, and they each have different performances, and like the single worst operation is sort of limiting the level of throughput we can have with harmonization. So making all the opcodes closer together, we are removing these single points of bottlenecks, let's say. So this is reason number one. The reason number two is that actually repricing will unlock some scaling from both headliners. So both EPBS and balls can have a meaningful impact on throughput. So with EPBS, we are giving more time for execution and also for data propagation. But there's also a caveat here, which is we are giving more time for execution than data. So we are increasing the time on both resources, but we are increasing more on execution. And for balls, we are introducing parallel execution and also state root calculation in parallel. But this is actually adding a cost, a data component cost to state operations, because now state operations will use block space, which is the block level access list itself. So what this means is that actually the relative costs of different resources will change. And if we don't adapt the pricing to meet those changes, then we are introducing bottlenecks not at the resource level, but on the whole resources. So for instance, if we don't reprice state growth as an example, we cannot really increase throughput, because if we were to increase throughput by which would be allowed by both EPBS and block level access lists, then we would increase state growth. And even though we have more time in the block for execution and for block for propagating the block, we don't really have more room for state growth. So the available budget for state growth we have is not changing. And so we really need to change the relative cost of this component for the other. And this is the same between the relative cost of data and compute and state access. So because now data will have to become more expensive in relation to both compute and state. And so without repricings, really the level of scaling we can get from the both headliners is limited. And on this note, then how do we think about repricing in Glamsterdam? So at the moment, the meta EIP, so the final version of the repricing meta EIP is not yet merged, because there are a few EIPs that are also not merged. But at the moment, we have 16 EIPs that are in some way related to repricing, which is a lot. So this can be a bit hard to navigate. But I think I'm starting to think of them as in these three categories, which I think helps to kind of put them in buckets and think about them. So on first, we have broad harmonization. So this is essentially EIPs that are changing a broad set of operations that all touch a specific resource. So for instance, we have one for compute, state access, state growth, and also for intrinsic costs of transactions. Then we have pricing extension. So this is more a targeted change in the pricing model. It could be just repricing a single opcode. It could be changing some component of the gas model. And usually this will either unlock some scalability or fix some specific misprice. So it's not a broad reprice, but it's more a targeted thing. And so we have this, for instance, for data, for state access, transient storage, memory, and also gas refunds. And the third one is supporting. So this is not actually repricing EIPs, but are EIPs that are somehow supporting the other EIPs. And for these, we have two for fixing rounding errors and also the multidimensional metering. And so now, in terms of prioritization, the way I'm thinking of it is, first, we need to do the broad harmonization. So this is where we will harmonize compute, state access, state growth, and data. So these are the 4 components that are really, really important for us to reprice, and we have to do them together. So we make sure that we are not introducing a single resource as a bottleneck. So we are harmonizing within the resources, or in another way, we are harmonizing each resource, so the operations in each resource, but also we are harmonizing across the different resources. So we are not leaving any bottlenecks on the table. And then once this is done, we can think of adding some pricing extensions that either address specific gaps or enhance scaling. And we can think of it like the removal of refunds from the block limit, which solves some worst case blocks, the size-based S-store, transient storage, rounding errors, etc. But I'd say like this first broad harmonization is really important to do it together, so that we don't create new bottlenecks. We don't leave these bottlenecks on the table. And so on the docket today, we have all these EIPs. So again, I will give 5 minutes each. And we will start with Ben talking about reducing intrinsic transaction gas. Ben, I will stop sharing and I will give the floor to you.
Okay. Send a request to share. Okay, let me bring up continue things open. Right. Yeah. Okay. So the intrinsic gas of a transaction is essentially defines the lowest amount that we can do, the lowest amount of gas we can use in a transaction, and therefore it directly determines transactions, max transactions per block, and also um, transactions per second. So it's quite high at 21,000 gas. So this looks to decompose it into parts, and then and also reduce it as that. Also, there's a weird gap in which might be factored into the 21,000 gas at the moment, where you can create an account um, as part of that initial transaction, and it's no different. You aren't charged any extra than if you don't create an account in that transaction. So this harmonizes that with core. So the transaction base cost drops to 4,500, although that's very decomposed. So if you do an ETH transfer, since you do an update on the to account and a warm, that's actually 6,000. But if you were doing like a contract call with no value transfer, then that would be your base cost, and you'd add the execution on. And then it adds the gas for a new account if you're creating an account as part of that. And it introduces a cold cost for no code. So if you warm an account and it doesn't have code attached, then when you're calling it, you're not having to load that code, start up the VM, the EVM, and then start processing opcodes. So that's cheaper. And then also to bring the call value cost. So at the moment, if you transfer value in a call, that's 9,000 gas, and instead it brings it down to match this, which would be 2,000. Two state updates, one for transferring from the sender, and one for receiving it. So it introduces a state update uh, at 2,000 gas. Sorry, 1,000 gas. And so on, this is sort of a 367% uplift in the amount of transactions you can do at minimum size. Although the equivalent gas based on all transactions is only 20%, because there's less of that that's used for ETH transfers specifically. If I can show you some graphs in here. So like a USDT transfer, that changes from the dotted line to this red line here. So it's not a huge increase in the amount of those you could do for like a Solidity transfer, which is much more gas efficient. Then it's a much bigger uplift. And for ETH transfers, it's like a huge uplift in the amount you can do. Yeah, that's essentially it. There's a lot in the proposal, sort of explaining it. Motivations. There's like, encourages ETH as money. It lowers the friction in transferring ETH and using ETH as part of transactions. So there's lots of good stuff. You don't charge it as call data, the transaction envelope, and you count the to and from addresses as warm because they're like in the transaction header. So there's no additional data. If I do the breakdown, where is it? Uh, yeah. So the breakdown is essentially EC recover at 3000 gas, a state update, which is updating the balance, charging the gas. So it's like a single leaf update counted. Um, and then no code. Oh, sorry, it does a charge for warming. And then no code warm, which is if you're an EOA initiating the transaction, then you don't have code that you're loading. That's where the 450 comes from. And then if you're yeah, there we go. Yeah, yeah.
Okay, Ben, I think your 5 minutes are up. But
Okay.
maybe I can give 1 more minute for comments. I don't know if there are any comments. Also, be free to use the chat, Ansgar.
Yeah, and then just to very briefly say it, because I think it's important enough, I also put it in chat. I think I really like the EAP in for the general, hey, we should consider also adjusting the base cost if we are repricing everything to be in sync. Just again, pointing out for people for whom that's not fully top of mind yet, with repricing in general, there's always this question, what do we anchor to, right? Because in principle, you could harmonize everything and then everything costs 1 gas, or you could harmonize everything and then all the operations cost 1 million gas each or something. Basically, like harmonizing just means relative to each other. So you still have to have like some sort of like absolute level at which all the prices are basically. And so we could also just choose that we rescale everything so that, say, at least the base transaction, I think we also now want to separate out transactions that do create new state at the recipient or that don't, but that the base transaction that does not create new state comes out at 21,000 again. That could be a reasonable choice. But basically, I think if we're not choosing to rescale everything to exactly that level, then I agree with the intention of the EIP that we should then also adjust the transaction base price.
Yeah, it's sort of the current prices in it are scaled to EC recover using the
Great. So I think if you have any more comments, please just put them in the chat. We are now moved to the next one, which I'm presenting. So I will just share again my screen. So this is I think it's one of the most recent EIPs. It was done together with Charles, and is about introducing warm account rights. So the innovation is essentially when an account is updated multiple times in the same transaction, the state root calculation can be batched, and all updates can be done in a single calculation. And my understanding is that this is the standard operation of all clients. However, users are paying the full costs of the gas call value or gas storage update if we are updating a slot. And so this doesn't match the actual resource utilization, because the first account update should be more expensive than the later ones. And if we can make this adjustment, making warm account rights cheaper would increase throughput on these specific transactions, so the transactions that would update the account multiple times. And the proposal is simple. So we will replace these gas call value and this gas storage update with 2 new parameters. So we have the gas cold account rights and a gas warm account rights. And the first account update essentially pays the cold cost, while any following account updates pay the warm costs. And we need to check whether the account is warm or cold, and by that we need to track whether any of the account fields were changed since the transaction started. And these repricing would impact the create2, the call opcodes, and S-star. So this is really short. So I'm giving some time for comments, and yes, if you have any comments, just let me know and we can discuss. Ben?
For the call account rate, I do have that adjusted in the EIP I previously presented. It sort of factors in that in terms of there is a warming cost which would go away, but the in it I do have the 2 storage rights charged the same regardless. There's no so there's an extra surcharge if you warm an account, but if it's warm, it doesn't become dramatically cheaper, other than the fact it starts dramatically cheaper. But and that's so that there's that stipend protection that exists in some contracts for recursion. So it still comes in about 2,000 gas, which means you can't do recursive calls if people are having. So it's like a DDoS protection.
Right. So I think that's a relevant point. So we still need to do some. So we still want to benchmark these and make sure that these costs make sense. But that's like a vector that we need to take into consideration, depending on the final numbers. Ansgar?
Yeah, just on this point, I personally think that if we are serious at least about making pricing changes to the EVM and maybe also continue to doing them beyond Amsterdam, I personally think we just have to be okay with breaking all the implicit assumptions that contract developers have made about specifics of gas pricing. And so it was never a correct behavior to use gas price assumptions, for example, for reentrancy protection, right? Like you have to have an explicit guard, and just making some assumptions that certain operations are so inefficient. I'm not sure, and I'm not 100% sure that I understood Ben correctly, but basically these types of patterns, I know they exist sometimes in the EVM, but again, this is just improper behavior anyway. It's just based on assuming the EVM would always be inefficient enough that these things would be expensive enough that would hold. I personally think we should bite the bullet of. Oh yeah.
I think it was suggested as like a thing. So like the Solidity at one point had a, you could call transfer, and it had put a gas cap on, so you couldn't do the recursion. So I think we'd break a lot of potentially large value holding contracts and they'd get hacked. However, I was just saying that I take that into account in the other one, and it's not, the price is dropped very significantly, and it should also maintain that assumed invariant. But I mean that's also where the pay code, people want to bring that in, is so that to also do that.
Right. So I think, conscious of time, I think we'll need to move to the other presentation. I know, Carl, you have your hand up, so I will ask, can you maybe add your comment in the chat?
Yep, okay.
I'm sorry about that. And I think now we have Guillaume talking about size-based storage gas pricing. So I give you the floor, Guillaume.
Thank you. Wait. Same thing happens every time. I look from my window. Here we go. Okay. Can you see it?
Yes, we can see it.
Okay, cool. Yeah, so that's an EIP that is quite simple. If you omit the fact that there's a transition involved, but the transition itself is quite simple. It's just trying to target those contracts. Oh, I don't know why Okay. It's trying to target those contracts that are effectively spammy, meaning they take a lot of space, but they don't really provide much value. And we have noted that some contracts were uh, so large that updating them was causing measurable performance issues. So that goes against scalability. And if it's a very useful contract, it makes sense to keep it running. But when it's just spam, it's counterproductive. And everything relies around like goes around the fact that it doesn't matter how much data you write to a given contract, the price is exactly the same. And the result is that the state bloat will increase not only with valuable contracts but also contracts that provide no value. And this is a scalability impediment, so we want to stop that. So the solution that has been proposed is about consisting in counting every storage slot inside a contract, and past the threshold, we start charging more gas per S store to disincentivize the filling of some very large contract. So the threshold could be moved over time. So currently would be only targeting a single contract on mainnet. But yes, if more spammy contracts come, we could change this threshold. Or if useful contracts grow larger, we could also move this threshold up. Yeah, so the biggest takeaway point here is that for most contracts, in fact, virtually every contract on mainnet except one, the gas cost would remain exactly the same. But yeah, one of those contracts would pay, it says incrementally more, but it's actually exponentially more per slot than we would yeah, like the goal is to keep them from doing, sorry, to make sure they stop doing this. So yeah, like the reason for this, and especially doing it now, it's simply because we do notice an impact of this specific contract on scalability, and we want to make sure it doesn't impede the progress in terms of scalability. But yeah, we also there are also other reasons that are more about the feasibility of it. It's quite easy to do. It's also having a desired effect, like good effects, like forcing people or contract designers to break their contracts into smaller pieces, which are easier to recompute, easier to expire, and ultimately easier to manage. So like I said, there's a transition aspect to it, and we just have to add a slot counter per account. There's no other choice than going over every single contract in the state and updating them. But for that, unlike the vertical transition, we would be using a smart contract, so it offers a lot of features, namely the reorg awareness that you could be using inside sorry, to handle reorg. So in that contract we would store the pointers, the pointers of the iterator, and just one last thing, it's compatible with the same sweep that has to happen in 29, 26, so we could do both in one go. Yeah, just to recap, but I'm also at time, so maybe if there's time for a question or yeah, just call it.
Yes, I think we are right on time, but I will give a one more minute for comments or questions if there are any.
So would this not be on the account, but be in a smart contract?
Come again?
The count would originally it was value on the account. Oh,
So
so
it's a
the
value that's added to the account, yes.
okay.
Yeah, Ansgar?
Ansgar?
Yeah. And just to say, right, like the attractive part of this, of course, would be that if we don't do this, then every contract, even one that has only like very simple storage, would basically have to pay for the worst case. They basically have to pay for kind of a Xen style kind of storage layout, which is very unfortunate and would be extra cost. So this is like a very attractive efficiency improvement. I personally still have some headache or like some worries about basically just the complexity. I understand you introduced it with simple complexity, but like I still have some headache about like the complexity of the mechanism, how easy it would be to like to establish to really be certain that A, the transition itself, and then B, also like once it's live, that there's no kind of ways to exploit it too much or no edge cases that we didn't cover. But basically, if we can get to a level of being certain about this, then in principle, I think it's a very attractive EIP.
So regarding the transition, it's a simpler version of the Verkle one, which has already been tested extensively. So yeah, I don't think. I mean, oh, okay. I know there's a lot of people who haven't looked into the Verkle transition that are scared about this, but honestly, given how simpler it is, I'm not too worried.
Okay, Ben?
Yeah, on transition, it would need to be coordinated in order to all the clients change prices at the same time. But I just like to say the original one was based on depth, and I much prefer this one based on count because the depth it ties it to a certain structure and assumptions with that structure, whereas the count doesn't doesn't assume an implementation detail. If you see what I mean.
You can go next, Tony.
Yeah, my question, I think Carlos already answered my question. I was asking what the threshold was that you had in mind there where only one contract was affected. Is that the Xen contract basically putting the threshold there?
Yeah, I'm trying to not name it, but yes.
Okay. Okay. And I was interested, yeah, this feels a bit arbitrary. It would be interesting to see how the distribution looks like because I imagine it's like very right skewed and has like a long tail, and then at some point you stumble across those very big contracts. So maybe we could even be more aggressive, right? But yeah, or have it like dynamically growing somehow. But this is not just thinking out loud.
I mean, it will be dynamically up to a threshold, but if you want to lower the threshold, yeah, I mean, Maria will have something to say about this. Doesn't make any difference to me. Will make a difference to you, the user, of course. But yes, that can be calculated if you want.
Yeah, the next one after Zen, I think, is USDT, so we'd need to be careful around there.
Exactly.
Yeah, I think once we have the benchmark data, we can start like putting numbers on the parameters, and then we can discuss more deeply what is the ideal thresholds there. Okay, conscious of time, we'll move to the next one. So now it's me again. I'll be presenting two EIPs. So I'll just share my screen again. Okay. So this one is the state creation harmonization. So essentially the motivation is, I think I explained this a little bit before, but if we don't change anything, higher throughputs in the EVM will essentially lead to more state growth because more transactions come in and more transactions that growth state will come, and so we'll have an acceleration in state growth. And looking at the more recent data, we can see that state growth has a median of 74 gigabytes per year. So we are adding a median of 74 gigabytes of new state per year. If we were to proportionally, based on the current block limit, if we were to proportionally project that to the 100 million block limit, this would be 197 gigabytes per year. So this will actually give us less than 2.5 years to reach the 650 gigabytes threshold, which is worrisome. And so this is the key motivation for why state creation should become more expensive now. But also, we recognize that state creation is itself not harmonized. So, for instance, creating new slots is more expensive than deploying new codes. And so we need to harmonize this better. And so the proposal is fairly straightforward. So essentially, we are setting a unit cost per new state bytes. And these costs targets an average state growth of 6 gigabytes per year at the block gas limit of 300 million gas units. So these values can be discussed, and the point where you put them will have a big impact on the level of repricing. But these essentially is trying to future-proof the scale. The scale we'll expect to have the next year, so we have enough time to have a more longer-term solution for state growth. And with these new costs, essentially, contract deployments will become 10 times more expensive. Slots will be around 3 times more expensive, and new accounts get an increase of 8.5. And there's a caveat here, which is because now contract deployments are so much more expensive, we are actually the limit on a limit on the size of the contract you can deploy from the transaction limit. So Fusaka has these 60 million units for a transaction. A single transaction cannot use more than that. And that limit and this pricing, we would be only able to deploy a 6 KB contract, so very small contract. And so for that, this proposal is also introducing an independent metering for the code deposit cost. So it's a simple version of multidimensional metering, essentially. And yeah, we still have 2 minutes. So if you have any questions, comments, I'm happy to take.
Yeah, I'm not sure how I feel about this. It mostly from the increase seems very large. I don't know.
Right. So I think the point where we can argue is this one, right? Like where are you setting your target? Maybe we can discuss that we can have more than 60 gigabytes per year, or maybe you can argue that the 300 million gas units is too aggressive, and then that will have a direct impact on the cost. But I think this is the points we should be discussing and not the level of increase, because the level of increase is in isolation. I don't think it's as meaningful. Like we should be discussing the first point.
Yeah, I mean, we could also factor in like, what's the improvements in hardware over that time as well.
Right.
It's just the user impact, would it make would trying to limit state growth that much with the prices, would it cause the user experience of the chain to become like, if somebody wants to get a new token, that'll create a new storage. Yeah, I don't know how I feel on this.
Storage slot is only 3 times, right? Like the worst is actually contract deployments, which I think it's sort of more manageable because it's something that is not done as much. For the new accounts, you could also argue that 8 times is too much.
I mean, I'm less probably less worried about new accounts and contract deployments than, well, obviously 6 kilobytes for contract, but yeah, than the new storage slots, because they're a more common thing that regular users would experience. But
Right.
yeah,
Yeah.
I don't know if it's, yeah. I'm not saying it's bad. I'm just saying I have concerns.
Yeah, it's something we need to think about. Okay, so conscious of time, we'll move to the next one. If you have any comments, please use the chat. And the next one is the state access harmonization. So here the motivation is essentially, we know that the state access operations, so reads and writes, have been deteriorating due to the increase in the state size. And we know that state access is a known bottleneck for higher throughput. In addition to these things, and we know that block level access lists and EPBS will impact the relative costs that state access has to data and compute. And so we need to reprice things to be first in line with the current performance of these operations, and second, in line with these two new changes that are changing the relative costs of these operations. And so the proposal is fairly simple. It's just we are doing a broad repricing on all state gas parameters or state access gas parameters, and we'll use state benchmarks to fit the final numbers. And this has an impact on S-store, S-load, the call opcodes, balance, self-destruct, and the X opcodes. And when compared with 8032, which was the proposal that Guillaume talked about earlier, this essentially would assume a worst case contract size. So we are not fully unlocking state access scaling. So if we were to implement 8032, we would be able to make some operation or some state access, or in this case, state access to smaller contracts cheaper than just implementing this proposal. But I say this proposal is the base, so we are doing a full harmonization, and then 8032 kind of unlocks this additional scaling by allowing us not to price on the worst case, but have that differentiation. And yeah, this is the proposal, so I'm happy to take any comments. I think we still have some time. Okay, if there are no comments, then I can stop share and we can move to the next presentation, which is from Carlos about contract bytecode by duplication discount. Carlos.
I made the same presentation like on Thursday. I'm happy to do it again, but if people was there and we prefer to discuss directly or something like that, I'm also happy to do that. Anyways, if you want me to do it, I can definitely do it.
Maybe what we can do is, like, is anyone on the call that really wants to see the presentation? Please raise your hand, and if not, we can just discuss it. Okay, so Ansgar is asking for a recap.
Sure. Yeah, so the recap or the TLDR is basically if we do all of the state gas price increases, what will essentially happen is that in things like deploying a contract, we are charging an outrageously unfair amount of gas to the user when the bytecode is duplicated. So nowadays, every single client, when they have to deploy bytecode that already exists, they charge the user the same price whether the bytecode is duplicated or not, but they actually perform the duplication, so they don't store the bytecode twice, which of course makes sense. Thus, it doesn't make sense for the user to actually pay for that, especially when a 24 kilobyte contract potentially will be like around $100 with the ETH price at 4,000, which is a considerable amount of money. This also paired with the fact that account creation costs will go up, and that we should indeed try to encourage let's say reuse templates and this kind of stuff, and also paired together with the fact that with Hans analysis we clearly saw that the 97% of the bytecode that it's deployed in Ethereum, it's basically like duplicated, so the contracts are just complete copies bytecode wise. I don't think it makes any sense to charge users that amount, but yeah, that's the deal they are basically.
And maybe a question then from my side on this. Again, one of those optimizations that I think makes a lot of sense. One unfortunate aspect here is that right with EOF, what we were thinking about doing was having like a nice separate code section within contract code. And then the code section really could be identical anytime you have the same contract deployed. Without this, obviously the problem is that like Solidity usually basically puts constants that are defined at deploy time into the bytecode itself. Not every contract uses that, but many do. So I don't know, tokens or something have the token name and the number of digits in the code, and so they are all slightly different from each other. These kind of things. So basically, I'm wondering right now, do we have a good feeling of like what classes of contracts this is basically usable for because of this limitation, versus kind of what classes of contracts cannot make use of that? Have we like does the Solidity team have a take on this? Would they, for example, then at least stop using constants in the code to more make use of this? Like, do we basically have a feeling for the kind of the practicalities around this limitation?
It would certainly, like all Uniswap v2 and v3 liquidity pools, for instance, they're all duplicated contracts, and they use the init code to set the value. It would encourage people maybe to use more standard contracts also, and then pass, because you could initialize like token name and ticker and so forth in the init code rather than in the contract itself.
I completely agree with what Bet said. I I don't think there's really any heavy pushback or any like issues. I think the only issue or discussion is more like the UX problem. But besides that, most of the contracts or contract accounts share the same exact bytecode. Anyways, if Han was looking at that, if I remember correctly, the number was 97%. So I think most of the people that deployed these contracts will definitely benefit from that. And if we can move towards safer and more common standards, I also think it's a victory. Anyone is free to, of course, keep deploying whatever they want. But if we can coerce to having more standardized things, it makes analysis of the state and a lot of stuff significantly easier to do.
Do we have any client-side feedback on are there any complexities around this? Because obviously, as you said, right, like in practice, everyone already deduplicates locally anyway. Is there any complexity around basically like making this now enshrined in consensus about like what is and is not duplicated, or is this kind of straightforward?
Well, the exact point of this EIP is to make it such that the implementation for clients is trivial, meaning it's the user who has the, let's say, UX burden, to put it on some way, to actually figure out which account holds the same bytecode or code hash as the bytecode that the user wants to deploy in this transaction, right? So this was chosen and done via access lists purely because on that way we don't actually need to make any crazy changes on clients. Of course, clients, in my opinion at least, could optionally provide this reverse map that goes from bytecode to addresses. This is something that a lot of third-party providers actually give you, to name one, Etherscan, basically. But basically, that's the smoothest thing for clients, at least in my perspective. Like they need to do very few stuff.
Oh, are you saying you'd additionally like to provide an option where you could just say copy this contract rather than having to put it all in call data?
I mean, I wasn't going that far. We can certainly explore that. I mean, you need to. I think you need to run the init code anyways. So I'm not sure to which extent it will matter because after running the init code, you already have the bytecode. So I don't think it's an optimization to load it from somewhere. Although you can of course do it if you want. What I'm trying to say is I had to choose between forcing clients to implement a reverse mapping, no matter what, to actually make them check if every single deployment is deploying bytecode that it already exists. Or instead, we have the access list approach, which moves the burden to the user and makes things significantly easier for clients. So I chose this route, of course, debatable, but yeah, this is to go for at the
Okay, so conscious of time, I'll have to wrap this discussion and we'll move to the last presentation. So Guillaume is talking about chunk-based code Merkleization. Guillaume, you can go.
Yeah, sorry, I was just trying to answer Carl about the transaction type as well. So while I load my presentation, I will just say that the converse sorry the transaction type means if you enhance further transaction types, you will not be able to inherit all of that with the new transaction type. So I think it's better to do it this way. Okay, so as I said that it's just done loading. I hope you can see it. Um, yeah, so there's this old EIP 2926 that was revived. It's about chunk-based code merkleization, and the idea is that the Vertical tree EIP had many advantages, but one of them was that it would introduce code chunking, and it came to like we realized in Berlin that we could actually do that in the MPT and already address some of the problems. Okay. Yep. And the problems being that first, there's currently a limit on the code size. You can only load, you can only write code that is up to 24 kilobytes. And removing this limit is a bit of a problem because it takes more space in the database that you don't necessarily pay for. I mean, you pay at deployment, but you still need to pay for the loading. If you only need 1 byte out of that byte code, you need to download. So you need to load everything into memory. There's a mismatch between what it costs to execute code and the size of the code, which could be 24 kilobytes or hopefully more. So the CIP and the code chunking in general is trying to address this issue that you only read one chunk at a time. There are other problems, including provers. It has been demonstrated that just doing Xcode size, just getting the size of the code means you need to load the entire code and get the size of that bytecode. So that's a good way to kill every prover, and in fact it has been done. And yeah, in general, we want, I mean, in several ACDs, people have come in favor of removing the code size. So doing chunking can offer this, like offers a solution to this. Oh, I forgot, of course, the code has to be attached in the witness. So if there's no limit in the code, your witness will also explode in size. So yeah, I already more or less explained what it does. It breaks the code into chunks and you only load one chunk at a time. So if you don't need to execute everything, you only load what you need to execute. You can do preloading and things like this, of course, but yeah, ultimately you can better manage resources, especially if you remove the code size. So what it does, it adds two new fields, the code size itself, so that you can perform the Xcode size operation without loading the code. And it adds a code root that contains every chunk inside a Merkle tree so that you can commit to this. And then, like I said, you only load code chunks that you need, and you pay for only the accesses you make. So it's more granular, it's better in terms of resource usage, in terms of witness size, and also in terms of price, because once again, you only pay for what you use. Yeah, so already covered most of that. Better developer experience, better scalability. You don't have to load a lot more code inside memory. It's got potential smaller bandwidth because of witnesses being smaller as well. And it removes the need for, it removes an attack vector. There's still the concept of transition. In fact, it's exactly the same as the one in AT32. They can be both done at the same time with exactly the same complexity. And yeah, it's just about calculating the code size and the code root. And then, of course, in every new contract, will already, upon creation, activate this and lift the max code size. That's also pretty much it. Ben, you have a question?
Yeah, if this is used as the actual internal representation for the clients, would it be significantly slower to load contract code? Because like 20, if it was in 31 byte chunks, then for a 24,000 kilobyte contract, if you used it all, would be like 800,000 reads. Is that correct?
Yeah, I mean, that's an internal implementation detail. Clearly, it would make sense to organize them by pages. So you could pull several code chunks together inside a single database key. So there's a sweet spot that will depend on the database system and the database model, where you can have several chunks pulled together and try to not load everything at the same time. Yeah, sorry, I kind of forgot the initial question, but overall, the idea is that it's an implementation detail, and the goal is precisely to reduce the performance impact of loading big code.
Okay, thank you, Guillaume. And we are on time. So I will just remind everyone that next week we have another call where we go through the remaining EIPs. If there are any more discussions or questions or comments, there's a Discord channel called EVM Pricing. I will ask you to go there and discuss. And are there any last comments or thoughts before we wrap up? Okay, so Ansgar?
Yeah, just one thing was that confused me. The 8058 that Carlos presented, I don't see it on the PFI list. Is that still going to be on there? Because as of now, it looks like, to me at least, that it's not proposed for Amsterdam.
The PR was approved by Stokes, but maybe it's not merged yet.
Okay, yeah. So I just wanted to check if it's in progress of being proposed, then that's fine. I just was confused that I couldn't find it. Awesome, thanks.
Thank you so much for joining, and yeah, we'll see you next week.
Thanks, Maria. See you next week.
Bye, everyone.
Bye bye.
Thank you.